Dear participants, hello everybody from all over the world. I wish to welcome you all to a lecture in the section Statistics and Data Analysis. My name is Alexander Schrijver from Amsterdam, and it is my pleasure to introduce the speaker, Professor Bin Dong. Professor Dong is Deputy Director of the Center for Machine Learning Research at the Beijing International Center for Mathematical Research of Peking University. The research of Bin focuses on mathematical modeling and computations in imaging science and machine learning. He is an expert in applying statistical and PDE methods to machine learning, image reconstruction, artificial intelligence, CT scanning, deep learning, and neural nets. The topic of Bin's lecture today is mathematical modeling in image reconstruction and beyond. Bin, please go ahead. We are looking forward to your lecture.
All right. Thanks, Alexander, for the nice introduction. Can you guys see the full screen nicely? Right.
Yes.
Okay. All right. And I would also like to thank the organizers for the invitation and putting together such a wonderful event, even with all the challenges. Today, I will talk about mathematical modeling into reconstruction and beyond. Hope you'll enjoy my talk. This is the outline of my talk today. I will start with a brief introduction of the background of image-based scientific discovery and the notion of computational imaging, which includes image sensing, reconstruction, and analysis. Then I'll focus on image reconstruction and review two prevailing mathematical approaches, namely PDE-based and wavelet-based approach. After this, I will present our work on addressing the connections between the two approaches. And in the fourth part of my talk, I will start going beyond mathematical modeling and embrace machine learning, specifically deep learning. In particular, I will present our work on drawing connections between deep convolutional neural networks and discrete differential equations and show what we can make out of such connections. Well, at this point, we should have a fairly integrated understanding of mathematical and machine learning methods. Then I'll come back to computational imaging. In particular, I'd like to talk about how we may integrate sensing, reconstruction, and analysis, the three main components of computational imaging, and discuss the potentials of such integration, challenges we may encounter, and some of the existing efforts along this line. With that, I will arrive at the conclusion of this talk. So now let me start with the background of imaging. As you may know, that scientific discoveries have been heavily relying on visual examination, while images are essential tools for that purpose. Let us first recall a well-known example in the history of imaging, which is known as the horse in motion. Back in 1874, a former California governor, who's also a racehorse breeder named Nathan Stanford, well, Stanford and his wife are also the founders of the Stanford University. Stanford had a theory called the unsupported transit, which said that there were indeed moments in a horse's stride in which all hooves were off the ground. It is not easy to prove that theory since the speed of a horse's movement surpasses the sensitivity of humans' eyesight, and also the shutter speed of the cameras back then was not quick enough. So Stanford sought the help from a pioneering photographer named Edward Muybridge and conducted experiments at Palo Alto in 1878. Muybridge created an imaging system using multiple cameras and wires as triggers. When a running horse triggers a wire, the attached camera takes a picture. This is the first time a rapid motion is captured by camera, and it proves Stanford's theory. So if you look closely at the video, you will see that all four hooves were indeed off the ground when all the feet are under the horse's thigh. The horse in motion is an early example of image-based scientific discovery. It consists of three key steps: sensing, which is the Muybridge imaging system; reconstruction, which is image formation; and analysis, which was done by human examination. Now, with significant advancement of information technology, we're able to do much better in all three steps. So putting them together is what we call computational imaging, which is now the discipline that supports image-based scientific discovery and decision-making. So taking CT, computed tomography, as an example, the CT imaging system collects cyanogram data, which is reconstructed to a CT image using a certain inversion algorithm, and it was then analyzed by another algorithm. So for the first portion of my talk, I will focus on image reconstruction problems, and I'll come back to the whole picture of computational imaging near the end. Now let me give a brief review of some prevailing mathematical models for image reconstruction. Image reconstruction can be written as a linear inverse problem. For many applications such as CT imaging, this is only an approximation. So here F is the data collected by the imaging system. A describes the forward problem of the imaging system, and eta is the additive noise. In practice, the problem is quite ill-posed, since the operator A can be singular or has an unbounded inverse. This is the biggest challenge for image reconstruction. It is widely agreed by image community that to resolve this issue, using regularizations or image priors is an effective approach. One profound mathematical approach for image reconstruction is what we call PDE-based approach. In the earlier days, people designed nonlinear PDEs that take the observed image or a coarsely reconstructed image as the initial condition. The solution of the PDEs at a certain terminal time t are the reconstructed images, presumably good reconstruction if the PDEs are well designed. Some well-known examples include the shock filters by Rudy and Nosher, the Perron-Malik equation by Perron and Malik, the anisotropic diffusion by Vickers, and the fluid dynamic models by Bartolomeo, Bertozzi, and Shapiro. Well, alternatively, you can design variational models, which generally has two types of terms. One is the data fidelity term L, that ensures data consistency, and the other is the regularization term R, that handles the ill-posedness of the problem by restricting the optimization within a reasonable function class. Some well-known regularizations include the total variation, or TV, by Rudy, Nosher, and Fatini, the convolutional model by Chambaud and Lyons, the total generalized variation by British, Kunish, and Pogg, and so on. These pioneering works generated a lot of interest and inspired a vast amount of research in using PDE in image processing and computer vision. And the key to the success of all PDE-based approach includes the adaptivity to image geometry and the preservation of crucial image features such as edges. Well, the wave frame-based approach takes a rather different route than the PDE-based approach. Wavelet systems are multi-scale systems that provide sparse approximations to piecewise smooth functions such as images. Therefore, non-redundant systems such as orthogonal or bi-orthogonal wavelets are most effective in image compression, where JPEG 2000 is a well-known example. Redundant systems such as wavelet frames are effective in image reconstructions because they're more robust to noise. Unlike PDE-based approach, which starts in the continuum setting and discretize the models later, wavelet frame-based models started at discrete setting. So here we use W denote the wavelet frame transform in the discrete setting. There are three typical wavelet frame-based models, namely the balanced, analysis, and synthesis model. Similar as the variation models, the models also have two types of terms, that is the fidelity and the regularization. And there are other transformation-based models beyond wavelet frames, such as curvelets and shearlets. But all these models have one thing in common, that is to enforce sparsity of the representation by penalizing, for instance, the L1 norm in the transformation domain, as you can see in all of these models. These models can be efficiently solved using optimization algorithms such as proximal forward-backward splitting, ADMM, and primal view, and so on. And the key to the success of wavelet frame-based approach is the multi-scale structure of the wavelet systems and their ability to sparsely approximate piecewise smooth functions. Well, after working with both approaches for a while, I started to wonder whether they have connections. However, what I often heard when I was still a graduate student was like this. The PDE people would say that wavelets does not have a geometric interpretation and often lead to oscillations or Gibbs phenomena in the restored images. While the wavelet people would say that wavelets provide a multi-scale sparse approximations to piecewise smooth functions, which are suitable to model images and performs better in practice than, for example, the TV model. Well, in fact, there were some earlier works, very inspiring works actually, that discussed connections between diffusions and wavelet shrinkage. For example, the pioneering works by Mazak, Vickers, and Cito in 2003, they addressed connections on 1D nonlinear diffusions and shift invariant Hart shrinkage, and a later extension to a certain type of wavelet frame shrinkage by Jiang in 2012. But nonetheless, the two approaches generally compete with each other, and there are still certain things that are not clear enough, such as the connections between variable models and wavelet frame-based optimization models. And what about other type of differential equations, such as shock filters or fluid dynamic models, or other wavelet shrinkage algorithms, such as those that were derived from various optimization algorithms? And finally, can we actually get new and helpful insight from all these studies? So this actually motivated us to look more into the connections between the two approaches. So now I will go over some of our main findings on the connections between the PDE and wavelet-based approaches. This is a joint work with my colleagues, Jianfeng Cai from Hong Kong University of Science and Technology, Qingtang Jiang from University of Missouri St. Louis, Dan Osher from UCLA, and Zoe Shen from National University of Singapore. The connections are built upon the connections between wavelet frame transforms and differential operators. A key observation is that there's a certain correspondence between the vanishing moment of wavelet functions and the order of differential operators. So let us first recall the definition of vanishing moments. Here you see that the definition in both continuum and discrete setting. Basically, a wavelet psi or its corresponding filter Q has a high order of vanishing moment. It annihilates polynomials of higher degrees. This actually makes them differential operator-like, so to speak. Before we make the statement more rigorous, let us first look at a simple example of hard wavelets. The indices of Q corresponds to the order of vanishing moment of each of the filter. Let us consider one level of undecimated hard wavelet transform for simplicity. The Taylor's expansion reveals the relationship between convolution operator with kernel Q and partial differentiation. So now if we scale each set of the coefficients properly, we can approximate the norm of the gradient with hard wavelet transform. Summing over all the indices will give us an approximation to the total variation. This approximation has a part that is the standard discretization used for TV. The other part is specific to HAR, which makes the discretization 45-degree rotation variant. And we know that it is generally better, meaning higher quality of the reconstructed image, for discretization to inherit the property of its continuum counterpart as much as possible. It is also consistent with our empirical studies. Now, let's come back to the link between vanishing moments and differential operators and make it more rigorous. In the continuum setting, this proposition states that the wavelet coefficients, which is the inner product of U and psi at scale n-1 and at location k, is the weak derivative of U up to a constant factor. And there's a 1-1 correspondence between the order of vanishing moment of psi with that of the differential operator. The link in the discrete setting is similar. This proposition states that if we conduct semi-discrete convolution between a function f and filter q, the convolution approximates differential operators of a certain order up to a constant factor c alpha, and the order of differential operator has a 1-1 correspondence with the order of vanishing moments of the filter q, like in the previous proposition. And to make the link more precise, we also extended the definition of order of vanishing moments to the so-called total vanishing moments, so that the corresponding convolution not only reveals the order of the differential operator it approximates, but also the order of the approximation. Well, proposition 1 is the key result that eventually led us to the link between variation models such as PDE and wavelet frame-based analysis model. Now let us consider the following wavelet frame-based analysis model, which is equivalent to the actual analysis model we use in practice and the variation model. In our work jointly with Tsai, Orcher, and Chen, the main result is the following theorem. It states that the energy functional E sub n of the analysis model gamma converges to that of the variation model. With gamma convergence, we also automatically have the relation between their minimizers in terms of their optimal values. Furthermore, any cluster point of the set U sub n star is an epsilon optimal solution to the variation problem. Well, the links between other commonly used variation models and wavelet frame-based models were also established by our follow-up studies, such as the works that I'm showing here. On the other hand, proposition 2 leads to a link between wavelet shrinkage algorithms and nonlinear evolution PDEs. We found that the link is rather general. So for any given evolution PDE that takes this generic form, U sub t equals to the generalized divergence of phi sub L of du and u, where this d is a vector of differential operator, we can always construct a pair of dual wavelet frame transforms, W and W tilde, and a shrinkage function such that the wavelet frame shrinkage algorithm is consistent with the PDE. If the PDE is well-posed nonlinear diffusion, we can prove that the discrete solution generated by the wavelet frame shrinkage algorithm converges to the solution of the PDE. Here, just a side remark that I've taken out the data fidelity terms since they're not essential in our analysis. We also found that by studying the connections, we can derive new wavelet shrinkage algorithms and PDE models. So, for example, we analyzed this natural accelerated wavelet frame shrinkage algorithm for general image reconstruction problem that is proposed by Li, Fan, Ji, and Chen in 2014. We show that it actually leads to the following PDE. What makes it special is the presence of both first and second order temporal derivative. This is a direct consequence of dependence of UK on both UK-1 and UK-2 in the discrete counterpart. Similar results were found earlier by Sue, Boyd, and Candice in terms of ODEs and was later extended by Wibisono, Wilson, and Jordan. Our series of theoretical studies clarify some of the misunderstandings in the literature. For example, we now know that wavelet methods have geometric meanings as well. Also, the PDE-based methods can be understood through the lens of sparsity. For example, you can now say that PDE methods also seek sparse representation in the transformation domain, where the transformation is discrete forms of differential operators. When you discretize differential operators, the underlying transformations are essentially filter banks, and the specific forms of the PDE, such as the nonlinear diffusivity, determines the type of nonlinear operators we conduct in the transformation domain. And normally we want to promote sparsity. This is pretty much how we drew the connections between PDE and wavelet-based methods. We were also able to design new and potentially more effective imaging algorithms. And more recently, these studies also motivated our works on the understanding of deep neural networks, which I will talk about in a minute. For a given image reconstruction problem, you may start with designing a variation model, a PDE model, or a transformation-based optimization model. But no matter where you start at this diagram you see on the upper left corner, you always end up in the discrete setting. So at the algorithmic level, what we eventually have is a solution mapping that maps the observed data F to a reconstructed image. This solution mapping F are often discrete approximations of differential equations, which is also true for wavelet frame-based solution mapping, as what I have discussed in the previous slides. And this is just a convenient perspective, making it easier to compare with machine learning methods. And for most of the mathematical models, the mapping F is handcrafted, meaning that we designed every major components of the mapping. For example, we may start with a variational model by choosing suitable regularization and fidelity term. Then we choose a certain discretization of the variational model to convert it to a finite dimensional optimization problem. And finally, we select a certain optimization algorithm, which leads to the solution mapping F here. As you can see, that this is a rather exquisite pipeline, and we have a tight control of each of the steps. The handcrafted solution mapping generally works well and has good stability and fully interpretable. However, it might still not good enough in practice. You may wonder, why is that? Well, I think this is mainly because handcrafted solution mappings lack adaptivity to specific data sets or to specific tasks of interest. And such adaptivity is generally difficult to handcraft, but very important in practice. So however, such adaptivity happens to be the strength of machine learning, specifically deep learning. So I'll come back to this point with further details later in my talk. So, but now let's first look at one example. For a typical handcrafted image reconstruction model, there are always some hyperparameters in the model that are crucial, but often data dependent, and such dependency is difficult to handcraft. Taking the nonlinear diffusion model for image denoising as an example, if we let the equation evolve for too long, everything will be smeared out, noise, feature, everything. If we stop too early, there will still be noise left in the image. So therefore, the terminal time t of the model is crucial, and it heavily depends on the noise level. What we know is that when the noise level is high, t should be presumably larger, but it is difficult for us to handcraft a formula describing such dependency. This is where deep learning can help us. From what I see, that a current trending research direction in image reconstruction and many other areas in computer vision as well is to combine handcraft modeling with learning-based model. This brings us to the study of deep learning models, especially deep convolutional neural networks or deep CNNs. The works that I'm going to present are done jointly with my colleagues Chenjun Li from Harvard University and our former students Zichao Long, Yiping Lu, Xianzhong Ma, and Ao Xiaozhong. Just a quick review of supervised learning. Its goal is to find a nonlinear mapping F between X and Y by solving the empirical risk minimization. For deep learning, the hypothesis set of the mapping F are deep neural networks, such as CNNs. And we know very well by now that such hypothesis set is quite effective in approximating high-dimensional mappings, and for many practical problems, both X and Y are indeed high-dimensional. We can find a solution mapping for image reconstruction as well, or using supervised learning. And studies show that learning-based solution mappings using deep neural networks may significantly outperform handcrafted models. So here's a table I borrowed from a work by Zhang et al. In 2017. In the table, BM3D and WNNM were state-of-the-art handcrafted methods, while methods on the right portion of the table, such as DNRD and the DNCN, are deep learning methods. You can see that deep learning methods beat traditional methods by a large margin. But the success of deep learning is not just limited to image reconstruction. It has significant impact in multiple disciplines of science, engineering, and medicine. Of course, we know now that deep learning methods have a lot of issues, such as robustness, but their success is undeniable. When I first saw the results of deep learning methods in image reconstruction, I couldn't help but wonder, how did they manage to do that? What did they do differently? And more importantly, what can we learn? What can handcrafted models learn from machine learning? I still have all these questions in my head, but I started by exploring structure similarities between deep neural networks with discrete dynamic systems such as ODEs and PDEs. Our motivations is that traditional methods and machine learning methods all provide solution mappings to image reconstruction problems, and most solution mappings of traditional methods are approximations to differential equations. So therefore, it was natural for us to compare deep neural networks and discrete differential equations side by side. Of course, another motivation that there might be a strong connection between discrete differential equations and deep neural networks was the success of residual networks, or ResNet, and the optimal control perspective on residual learning proposed by Wei and Yi. Before ResNet, it was difficult to train a neural network with a few dozens of layers. ResNet tells us that if we do residual learning, like was shown by the formula here, we can train a neural network with hundreds of layers and significantly outperform the benchmarks at the time. Then Wei and Yi beautifully observed that ResNet can be interpreted as the forward order digitalization on an ODE system. So to this day, the residual structure is still one of the most commonly used structures in deep learning. To me, this is a strong indication that exploring structure similarities between deep CNNs and discrete differential equations can be beneficial. In our work in 2018, we showed that not only ResNet, there were other deep networks that adopt the idea of residual learning, such as PolyNet, can be interpreted as different discretizations of ODEs. Some ResNets with randomized structures, such as stochastic depth, are discrete approximations of SDs. This made us wonder if we could use discrete schemes of ODs and SDs to generate novel and effective deep networks, and we call this type of networks ODNets. To demonstrate that this can be a viable approach, we introduced a new network called LM-ResNet, which is constructed using the linear two-step method. Here, the scalar alpha k, together with all the parameters in F, are trainable parameters. A simple modified equation analysis reveals that LM-ResNet has one more degree of freedom than the ResNet. That is the parameter alpha k, which is able to dynamically balance between the first and second order derivative of x. We know from earlier studies on network accelerated algorithms that putting bigger weights on the second order derivatives of x can speed up the dynamics. So of course, this is not rigorous since f may not be the negative gradient of potential, but our intuition matches with our empirical studies. First of all, on the famous image classification benchmark known as the ImageNet, the LM-ResNet outperforms ResNet with the same number of layers, meaning almost the same number of parameters. On the other hand, the LM-ResNet managed to achieve a comparable test accuracy as ResNet with only half of the layers. One way to look at this is that if we view the network as a dynamic system that processes image data, then LM-ResNet processes data faster than ResNet because of the presence of the trainable parameter alpha k. But of course, you may now wonder, if the actual learn alpha k indeed helps to speed up the information propagation. To validate this empirically, we plotted the learn alpha k's in the bottom right figure. You can see that most of the alpha k's are negative, especially when we go deeper in depth. This means that LM-ResNet indeed places a bigger weight on the second derivative of x in deeper layers. This enables it to accelerate the information propagation, while ResNet has no such flexibility. There were many follow-up studies along the same line of research, which I won't have time to discuss today, but you can find a brief review of them in my preceding paper. While OD-nets explore structural similarities between DNNs with discrete ODs by relating temporal discretizations with different designs of residual structure, PD-nets tend to look closer at the dynamics F. PD-nets are deep CNNs with architectures inspired by numerical PDEs, or physically informed, so to speak. By training a properly designed PD-net, we hope to achieve two objectives. First one is to estimate a PDE with an interpretable form that best describes the observed data. And second one is to enable fast simulations. This problem is actually a typical inverse problem, often called system identification. This is a very active field, especially after the recent progress of machine learning. So here I'm just showing a few examples. For given observed dynamic data, PD-nets assume certain prior knowledge on the hidden mechanics that drives the dynamics. We assume that the dynamics can be approximated by a nonlinear evolution PDE with a known maximum order, for instance, second or fourth order. We also assume that the nonlinear function f has only simple operations. For example, we assume in our studies that f has only addition and the multiplications of its variables, which makes it a multivariable polynomial. Although this may seem too restricted, in fact, this already covers a lot of known PDEs. With these assumptions, we can now define our PD-nets. The idea is to use finite difference approximations to discretize the PD and use the corresponding discrete dynamics as the backbone, and then specify the learnable components of the dynamics. We discrete the PD using finite differencing and introduce a deep symbolic network to approximate f. Then we have an iterative scheme as shown by the formula here, which is essentially a deep CNN. The trainable parameters are the convolutional kernels that correspond to the finite difference approximation, and the parameters in the symbolic networks are trainable as well. So we call this type of deep CNNs the PD-nets. But one crucial components of the PD-nets is the approximation of spatial derivatives by convolutions. If we do not place any constraints on the convolution kernels, these convolutions may not approximate differential operators at all. Well, this will make the trained PD-net uninterpretable. This is where parameterization 2 that I talked about in the previous section comes in handy. If we want to control the convolutions to approximate a certain differential operator with a certain approximation order, we can simply control the constant C alpha by, for instance, letting all the one specific C alpha to be non-zero. And now, from now we will denote these vectors C alpha as the moment matrix just for convenience. The moment matrix is just a convenient tool for us to enforce linear constraints on the evolution kernels, on the convolution kernels. For example, if we want to approximate partial x with convolutions using a 3x3 kernel, what we need to do is by using the following three matrix constraints on the moment matrix. The third one gives us a deterministic kernel, while the first two are learnable approximations. The stars label the unconstrained slots. The more stars means the more degree of freedom we have for the learnable filter Q. Our empirical studies showed that having learnable filters help with the estimation of the analytic form of the hidden PDE, and it also enables more accurate simulations. And similar ideas was also used by some later studies. For example, Barr et al. Used learnable finite difference approximations to solve PDEs. Chabot and Pog used learnable discretizations for total variation. Alt et al. They give a more extended discussions on the connections between numerical schemes of PDEs and neural networks. As a proof of concept, we conduct experiments using Burger's equations and also a couple of other equations in our paper as well. So here we do not assume that we know it's Burger's or whether it's parabolic or hyperbolic. All we assume is that the maximum order of this PDE doesn't exceed 4, and the nonlinear function f is a certain polynomial. This is the result of model recovery, the leading terms of the symbolic network after training are given in this table. You can see that PD-net is able to accurately approximate the ground truth. Here, throw PDE-net means that we cheated a little bit by using a fixed discretization that is stable for burgers, which we're not supposed to know. The estimation by PDE-net is even more accurate than the frozen PDE-net, which assumes more prior knowledge on the hidden PDE model. This shows that having learnable discretizations of differential operators not only require a weaker prior knowledge on the PDE to be discovered, but can also make the estimation more accurate. Well, since we assume that the maximum order is 4, while burgers is the second order PDE, we also have some remainder terms, but they're all relatively small. Once the PDE-net is trained, we can use it for simulations using unseen initial conditions without retraining. Since the PDE-nets are CNNs, the simulation is very fast using GPUs. The plots tell us 2 things. One is that using learnable discretizations, that is, the PDE-nets, as shown by the orange regions, they generate more accurate simulations than using pre-selected discretizations, which is the frozen PDE-net associated to the blue region. Second is that using layered training, that is training the PDE-net with multiple delta T blocks or time steps, helps with finding a more stable spatial discretization, which in turn helps to generate more stable simulations. Well, the studies on both OD-nets and PDE-nets made us believe that the incorporation of differential equations or physics for any fundamental principles is beneficial in general. Here's a simple experiment on machine learning-based accelerated simulations of PDEs. The main objective is to learn an operator F theta, typically a neural network that approximates the flow maps between 2 snapshots. I'm going to compare the approximations of F theta with UNet, the Fourier neural operator, and PDE-net. UNet is a black box model with an encoder-decoder structure, assumes no knowledge on the underlying PDE, and has the most number of parameters. The design of the F and O is motivated by Green's functions, which incorporates certain knowledge on the PDE, while PDE-net assumes the most knowledge on the underlying PDE and have the fewest number of trainable parameters. The results are kind of expected because if you want to solve a PDE, your algorithm better use as much knowledge of the equation as possible. It's obviously not a good idea to assume no knowledge of the PDE that you want to solve. As we can see from the plot, the PDE-net has the lowest prediction errors, FNO is second, and UNet is the worst. The required number of trainable parameters is exactly reversed, where the PDE-net needs the fewest number of parameters. I think now the community of scientific machine learning gradually picked up a general strategy to effectively combine mathematical modeling with machine learning. Here, I summarize it into a workflow which I mostly follow during my own research, but different people may have very different perspective on this. It goes like this. So for a given problem of interest, you can start with your favorite algorithm, which is most likely a discrete dynamic system. For example, for image reconstruction, it could be a solution mapping, constructed from a discretization of a given PDE. And then you need to identify the components that is hard to handcraft. For example, the dependence of hyperparameters with the input image. And then you need to approximate such dependency using a properly designed deep neural networks, and that will make the solution mapping learnable. And then you need to select a certain loss function, either supervised or unsupervised, and a certain training algorithm, to train the parameter. And the same workflow can be applied to problems in other areas as well, such as in scientific computing and the rising field of AI for science. Now, I think it is safe to say that we have more powerful tools that enable us to do things we couldn't do well in the past. Let's come back to computational imaging and see what we can do now with these new tools. The work I'm going to present in this section is jointly with my colleagues from the Mass General Hospital of Harvard University, George Fakrin, Konstantin Chenzheng Li, and Dufan Wu, and also my colleagues from UC Santa Barbara, Xu Yang, and my current student, Yu Shen from Peking University, and my former student, Yufei Wang, who's now a graduate student at Carnegie Mellon University. So for a long time, we have been seeking for general purpose computational imaging systems. For example, compressed sensing specifies a rather universal sampling strategy to facilitate a robust image reconstruction. But such universal sampling strategy may not be optimal to each subject of interest or to a specific downstream task. Now with the advancement of machine learning, we can now design special purpose imaging systems to achieve possibly unrivaled performance comparing to general purpose systems. This has become an emerging area in computational imaging and has vast potential applications. So to achieve special purpose imaging, we need to integrate all the three components of computational imaging. This has been made possible, or at least much easier than in the past, by deep learning. It is mainly because deep models are effective in approximating complex high-dimensional mappings, can make very fast inference, and are differentiable. These attributes of deep models makes it tractable to do end-to-end training of the entire pipeline, meaning that we can now have a way to jointly train theta 1 for sensing, theta 2 for image reconstruction, and theta 3 for image analysis. Well, of course, this also brings about great challenges in model design, data collection, optimization, and theoretical guarantees. But still, it's an exciting research direction for computational imaging. There has been some pioneering works along this line of research that tries to integrate part or the whole pipeline using a collection of tools from applied mathematics, physics, machine learning, and so on. For example, it could combine image reconstruction with image analysis. The benefit of doing so is twofold. One is to improve the accuracy, since any image reconstruction algorithm inevitably introduces bias that can negatively impact on the downstream task. Therefore, it is potentially more effective to grab information directly from the measurement data. Secondly, from the standpoint of improving image reconstruction itself, we have been using generic image quality metrics such as the PSNR, peak signal to noise ratio, or structure similarity SSIM to evaluate the quality of the images. However, such generic metric can be very misleading. Here's an example I borrowed from Professor Stevens' slide, who is a medical professional at the Johns Hopkins University. It shows that the CT image on the right has higher SSIM, meaning better than the CT image on the left. However, the image on the right missed out a key feature, which is the long nodule due to over-smoothing by the reconstruction algorithm. Well, this example shows that we cannot simply rely on generic quality metrics such as SSIM. We should have a quality metric that is conditioned on the downstream task. So now with machine learning, this objective has become much easier to achieve. What I'm showing here are the three earliest works that I know trying to achieve task-dependent image reconstruction, where the work Wu et al. In 2018 is a joint effort with my colleagues at Mass General Hospital of Harvard University. Let me briefly describe what we did in this work. So our goal is to combine CT image reconstruction at human chest area with long nodule detection. Our idea was extremely simple. We first designed a deep CNN that was modified from one of the most commonly used handcrafted CT image reconstruction algorithm by introducing a few learnable components. Then we attached this network with a CNN, very simple one, that does image recognition, that is to label the location of nodules. The two networks were first pre-trained separately with individual supervised losses. Then the two networks were trained end-to-end using only the loss for nodule detection. So we observed from our empirical studies that there was an improvement on the accuracy of nodule detections, since now the reconstruction network is cooperating with the detection, the reconstruction network is cooperating with the detection network by extracting information directly from the raw data. And more interestingly, if you examine the reconstructed CT image closely, it appears that the reconstructed network does a lot more regularization inside the long region, comparing to the outside of the long region, which is something traditional reconstruction algorithms or standard deep models wouldn't do intentionally. I think this is because our reconstruction network knows that the images it reconstructs will be used for nodule detections, and thus it shouldn't care about the regions outside the lung area and focus more inside the lungs. Well, although this is only a simple proof of concept study and can be improved in multiple ways, it shows that combining reconstruction with analysis can be beneficial. You may also combine sensing and reconstruction to make the sensing have a dependence on the imaging subject and the reconstruction algorithm as well to achieve better imaging quality. For example, in our work with Shen et al., which just appeared this year, we showed how deep reinforcement learning can be applied to city imaging to achieve personalized scanning. This is essentially an optimization problem, a very tough one actually. What we're optimizing for each imaging subject is the angles of projection and the dose allocation for each angle. We want to maximize the imaging quality while keeping the total dose within a certain range. This problem can be formulated as a mixed integer programming, which is a well-known NP problem. We reformulated the imaging procedure into a Markov decision process and solved it using a deep reinforcement learning algorithm. So unlike, for example, compressed sensing that gives a generic sampling plan, which is the same for all subjects, our method generates different scanning plans for different subjects so that the image quality is maximized for each subject. So finally, a group from Stanford University, Weinstein et al., they're also trying to combine all the three components for optic imaging. They call it deep optics. If you're interested, you can look at their paper. And my group are also working on the integration of all the three components for CT imaging. So now let me briefly conclude my talk. Then maybe I'm ready for some questions. Well, I have talked about the role of computational imaging, the two prevailing mathematical approaches for image reconstruction, namely the PDE-based and wavelet-based approaches, and also their connections, and also the understanding of deep learning and how we may work with it in practice. Well, by looking into the future, I would expect more extended studies on the combinations of handcrafted and data-driven modeling. And for computational imaging, I would expect to see further advancement in special purpose imaging systems realized by integrations of image sensing, reconstruction, and downstream tasks. With that, I conclude my talk, and thanks for listening.
Thank you very much, Bin, for your very nice and inspiring lecture. It seems the audience cannot ask questions.
Oh.
I might have a question because deep learning is quite famous also because they're applying to Go, to games. Do your methods apply to such problems too, or?
What I mostly do is to apply machine learning to scientific computing and also computational imaging. I think it's more fun to do that. Yeah, but I'm not
serious.
Yeah.
Yeah. Okay.
I think yeah. Go ahead.
It's a wide area, so you cannot. This is just part of it. Okay. Thank you once again, and I close the session with thanking also the audience for being there.
All right. Thank you, Alexander. Okay. Bye.